Okay, I think we're ready to get started. Welcome everyone to Wednesday night at the lab. My name is Elizabeth Moore, and I'm an employee here for the UW-Madison Biotechnology Center. On behalf of the Biotech Center, UW-Madison, Division of Extension, Wisconsin Public Television, and Wisconsin Alumni Association, and the UW-Madison Science Alliance, I would like to thank you for coming out tonight to Wednesday night at the lab. We do this every Wednesday night, 50 times a year. Tonight is my pleasure to introduce Till Wagner. Tonight, Till will share about how sea ice impacts the world. So we have 5 famous questions we ask every Wednesday. And so the first one is, where were you born?
I was born in southern Germany, in Bavaria, north of Munich, in a small town called Aichach.
Oh, very interesting. Where did you go to high school?
I went to high school in the same area in another small town called Schrobenhausen, and the high school was called Gymnasium Schrobenhausen. Yeah.
Very cool. Where did you go for your undergrad?
I left Germany from undergrad and went to the UK, and I did my undergrad in physics and philosophy at the University of Bristol.
Oh, awesome. You hit my 4th question. And lastly, where did you go for your advanced degrees?
I left Bristol and went to the University of Cambridge to do a master's in applied mathematics. And then I stayed at Cambridge and did a PhD in applied mathematics, mostly applied to climate questions. And then I went to San Diego, to the University of California, San Diego Scripps Institution of Oceanography for my postdoc. So I spent 5 years as a postdoc there. And then I actually had a short stint, 3.5 years, in North Carolina as faculty at the University of North Carolina, Wilmington.
So all over.
Yeah.
So awesome. Well, ladies and gentlemen, please join me in welcoming Till Wagner.
There's a chat here. Hello from Belgium, Tom. Okay. Okay, welcome. It's a great pleasure to be here, and I'm excited to do this in person. Still feels somewhat unusual. Yeah, well, these intro questions are actually very helpful. That's sort of how I typically start. I've been at the University of Wisconsin-Madison for a year now, pretty much exactly, since July 1st last year is when I started. And I'm very excited to share some of my insights into sea ice. And I've structured this talk a little bit about why we should care about sea ice, what it really is to start out with, and a little bit less about my own research, but I will touch upon that at points. I will highlight my research at points. It's just, my research can be quite, I don't want to say tedious, but it's very specific. So I wanted to also give just sort of more of a broader insight here. So let me see whether this, oh, no, it doesn't want to cooperate anymore. Okay, so just to set the stage, we have 2 polar regions that are covered with sea ice to large and smaller extents. There's the Arctic region up here, and there's the Antarctic down here, and they are geographically quite different. And for the geographers in the room, I apologize, but this is quite crucial here. There's a couple of crucial points to my talk here. This is looking at the southern hemisphere, sort of at the bottom of the globe. And what you will spot is that the Southern Ocean, which is this region here, is dominated by this landmass, which is the Antarctic continent. And the Antarctic is literally a continent covered with snow. And that snow falls over thousands and thousands of years. And over that period, it condenses into ice. And that's what we call land ice. So this is land ice, and then the Southern Ocean around it freezes over in the winter, and that's what we call sea ice. And I'll get into more detail about that in a second. But first, here we have the Arctic. So this is now looking down at the globe. And there's, for example, there's Greenland here, North America, Siberia, Europe. And the Arctic is marked by this Arctic basin, which is an ocean. And so the type of ice that covers what we think of Antarctica and the Arctic couldn't be more different. So this is an illustration from National Geographic, and it basically shows you the Antarctic continent with sort of a cake slice taken out of the ice cover that sits on top of the Antarctic continent. And what's fascinating to me always is that on average, this ice cover here is about 4 kilometers thick. So this is a huge amount of ice that sort of sits on this landmass. And what happens is that the ice behaves like a viscous fluid, almost like honey over time scale of millennia, of thousands, tens of thousands of years, and it sort of will flow off the landmass into the ocean, and then breaks off at these outlets, which are called ice shelves here and here, or if they're narrow valleys, they're called glaciers. And that's how they flow into the ocean and then break off, and that's what we call an iceberg. An iceberg is a broken piece of land ice that floats around in the ocean. Very different to sea ice. And so sea ice is what we see here. This is a photo that was taken during one of our field expeditions to the Arctic Ocean. I think there's me in the little gray with the funny hat on. And so sea ice is the polar equivalent of lake ice. It is what happens to the surface of the ocean when the temperatures in the winter drop below freezing. At some point, the surface of the ocean, just like the surface of our lakes here, freeze over and form sea ice. The sea ice is much less formidable. It only reaches thicknesses of 1 to 5 meters. It moves around. It's always blown around by the winds or floated around by the ocean currents, and it will renew itself every seasonal cycle. So I think I have an animation here. These are great animations from NASA that shows us the seasonal cycle of the Arctic sea ice. If I can get it to start. So it started here in the summer with very little ice, and then it grows out to cover a region that's larger than Russia, and then it goes back down to roughly 4 million square kilometers and back out to something like 60 million square kilometers. Every year does that. So it's this huge annual cycle of sea ice growth and retreat. The Antarctic actually does the same thing, but now it's kind of the reverse, right? The Arctic is land around and the ocean in the middle that grows with sea ice every year and melts back again. So the center of the Arctic has for hundreds, probably thousands of years been ice covered all year round, right? It's so cold that all that ice doesn't completely melt away, but it does get moved around. So none of the ice is really older than maybe 5, 7, 10 years is like the oldest that sea ice gets. In the Antarctic, I think this is a much slower animation. Here, this is sort of this is the maximum extent of sea ice around the Antarctic in August. This is an example from 2009, and then you will see as we go. So obviously this is 6 months reversed. So minimum sea ice will be hit around March. So you'll see as we approach the austral summer, almost the entire sea ice cover disappears every year, down to 2 million square kilometers. A little bit is always left here in the Weddell Sea and in the Ross Sea typically, but then it expands again. So it has this huge seasonal cycle that's even a lot more pronounced than in the Arctic. So we can actually take, and I apologize, I'm sort of moving around my Zoom things here. It's a little hard to navigate. Sorry. Okay, so this is the Antarctic sea ice extent over the course of the year, right? So I shifted it by 6 months. You can see a line here on January 1st. So because I wanted to compare it with the Arctic in a second. But what you can see is that in the winter months, it extends to 20 million square kilometers and it almost melts completely and it recovers. Every year it does the same cycle. Now, every colored line corresponds to one yearly cycle on this plot, okay? And they are colored by the year they're taken. So the most yellow, and I apologize, it's quite small, most yellow is 1979. That was the beginning of the satellite era. That's when we started being able to measure this accurately. So 1979, we have a very yellow line, and then it goes up to 2022. And note that there is no specific trend in this at all, right? It doesn't look like this has changed over the decades, over the last four and a half decades. Now let's look at the Arctic. If I can move my slide. This is the Arctic sea ice extent. It doesn't extend quite as large. The Antarctic gets up to 20 million square kilometers. This only goes to 16, and it doesn't go down as much because you have that winter ice that sits in the center of the Arctic basin. It also has a bit more spread. It's a little bit more spread out between the years. But what's really fascinating is if I color this by year, and the colors are a little muted here on this projector, but you can see that the yellow lines were up here and it's getting darker and darker. And this is what we refer to when we talk about the disappearance of the Arctic sea ice. That is what, and it's specifically pronounced in the summer months. So it's every year, September 16th, the science community comes together. It's like, what's the sea ice minimum? Are we reaching a new low? What's happening? And the record minimum right now, oh my God, sorry, this just exploded. Oh, let me go back here. Apologies. Like climate catastrophe on my screen here. You can see it happens also in the winter, but it's most pronounced in summer, and it's gone from about 8 million square kilometers in the early 80s to about half of that. So over the last 45 years, roughly, the sea ice extent, minimum sea ice extent in the summer has lost about 40%. So we can look at this from one other perspective, and this is maybe a plot that some of you may have seen in some shape or other. So we've started in the 80s, 8 million square kilometers, and it's decreased by every decade. We lose another 10% of that original value. And to illustrate this graphically a little more, this is what it looked like, the sea ice in the summer in September 1984, just a couple of months after I was born. And then this is what it looked like in 2006, in 2012, when it reached its temporary minimum, record minimum. And the whiter the color, the older the sea ice. So the very white ice here is 4 or 5 or more years old, and the other sea ice is only a couple of years. The faintest shade is just a 1-year sea ice that's frozen that past winter. And you can see that almost all of 90% roughly of that multi-year ice has disappeared. So the ice cover is getting smaller, but it is also getting younger. It's getting less thick. So we have about 40% of area reduction over the last 43 years, and about 75% of volume reduction of sea ice. And so these are quite striking figures, right? And I think it's also just, it's just such a vivid image of this huge ice cover that is somehow not as large anymore because of climate change. And so that's, I think, why it also stands out as something that we really care about. Now, why else do we care about sea ice? And let me start out with the inverse. Why do we not care about sea ice? We do not care about sea ice when it comes to sea level rise. And this is, I do want to clear this up, because what happens is that sea ice is already floating in the ocean. And so it's a little bit like your cocktail glass that's filled with water. It already has displaced the amount of volume of water that it will fill when it melts. So when it melts, it just fills in that that volume, and it doesn't raise the actual level of the sea level. So that's why, that's the same principle why you do not sit at the bar freaking out all night that your cocktail will flow over when the ice melts and you're not drinking it fast enough, right? The reasons why you drink your cocktail faster are others, not sea level rise. So that's an important point about sea ice. What does lead to sea level rise is when land ice melts. So all that mass that sits on the Antarctic continent contains about 60 to 70 meters of sea level equivalent. If all of that melted, it would raise sea level 60 to 70 meters because it sits on land and it flows. It's like adding water or ice cubes to your cocktail when it's already full, okay? And so that's why we care about the Antarctic melting in terms of sea ice, sea level rise. And the Greenland ice sheet has the same property. But sea ice is just floating. We do care about it for a number of other reasons that are extremely important for the climate system. And one of those reasons is what we call the albedo effect. And so if you look at, this is a picture that was taken, oh, I have a length scale hidden here. So this is about 500 meters. This picture was taken by a photographer from the helicopter that we were flying over the Arctic sea ice edge. So this is the edge of where the open ocean meets the frozen ocean. And what you can tell immediately is that the white area is a lot more reflective than the dark area. So the albedo effect means that a lot of the sunlight that hits the sea ice surface gets reflected back out, whereas much more of the sunlight that hits the open ocean gets absorbed. It's a little bit like wearing a white t-shirt versus wearing a black t-shirt on a hot day out. You're going to get a lot hotter with the black t-shirt because you're absorbing all that energy. Whereas in the white t-shirt case, you're reflecting a lot of it back. So now what happens is that we are replacing a region of the Earth that was covered with our white ice, and we're just replacing it slowly with dark open ocean surface. And so as a result, we're absorbing a lot more heat. And in fact, the Arctic is, as a result, heating a lot faster than the rest of the globe. So we were interested in how this is the Arctic surface air temperature, anomaly meaning the change from the mean over the last 100 years. This is work that a postdoc, Mark England, working with me did last year. He was working with me and colleagues at the Scripps Institution of Oceanography. And so what you can see is that especially since the 80s, the Arctic has warmed by 2.5 degrees, whereas the globe has only warmed by about 1 degree. And a lot of that is due to that increased absorption of heat when you replace a white surface with a black surface. So it's a little bit like taking a cooling pad off the top of the planet and just absorbing a lot more. So it exacerbates global warming in that way. It also changes atmosphere and ocean circulation. So this is climate model simulations, and I'm not going to go into the details, but what they've done is basically looked at what happens to the sea surface temperature when you remove the sea ice. And you can see you get warming up here, but then very interestingly, you actually get cooling down here. And what they realized was that if you suddenly remove the sea ice, which is what they do in this model simulation, they suddenly remove the sea ice, the strength of the Atlantic meridional overturning circulation goes down. So this is the AMOC, and a part of the AMOC is better known as the Gulf Stream, right? So the Gulf Stream then sort of forms part of this meridional overturning circulation, which flows up here in the surface, and then the water sinks and returns at depth. And that is a big ocean current that's very important for the global climate system. And it appears that if you remove the sea ice, it actually somehow impacts the strength of this ocean current. And it's to do with how the formation and the melting of sea ice actually impacts the stratification of the upper ocean and how much you can produce heavy water at top that can sink. I'm not going to go into the details, but I wanted just to show this, that sea ice actually has many impacts, even though it doesn't raise sea level. Another one is that this heat anomaly that I showed you, that the Arctic is warming faster than the rest of the globe, through winds and other heat transport actually also gets translated even to the tropics. So this is work that Mark did in 2020 before he joined my group. And what you can see here is that if you remove sea ice in the Arctic, you get about a 1 degree or so warming signal all over the tropics. Yeah, and I'll get back to that in a little bit later in my talk. Yeah, there is a really fascinating effect, is that if you remove the sea ice, just the sea ice, don't do anything else to the globe, you will warm the globe all over. And the bottom panel is if you remove the sea ice in the Antarctic. Now it's tricky to just remove the sea ice in a global climate simulation, but I will get back to you to that. Yeah, but the point here is that the sea ice has impacts all over the globe. Why do we really care about sea ice? Well, a lot of people that I talk to really care about sea ice because it is the habitat and predominant living feature for a fascinating ecosystem. And the flagship species, of course, is the polar bear. And the polar bear uses the sea ice to hunt famously, and it is sort of its central habitat is this region and the coastal regions around the Arctic Ocean. And the polar bears are vulnerable. They're not threatened as such yet by extinction, but they are vulnerable. And there is an expectation that they might decline by up to 30% from 2050. There's big error bars on this, and they are also doing quite well in some regions. In some ways, life becomes a little easier if it gets a little milder, but overall, they do need the sea ice to hunt and to do well. One interesting thing, and I tend to show this to my global climate change class, is that the grizzly bears have been migrating further north as a result, and the polar bears are more restricted in their habitat. So there is some indication maybe that there might be some crossbreeding, which leads to the grizzly bear, which I just find amusing. Also because apparently when two species like that mate, the result is bigger, the offspring is bigger than either parent. So you know this about the tiger and the lion, the lion or the liger is bigger than either parent. So this is just sort of a fairly irrelevant anecdote on the side. Grolar or grizzly bears. Now, another reason why we really care about the Arctic region is because it is, we might think of it as barren lands, right? But it is actually populated quite extensively by native Arctic peoples, and who have over the centuries also finally adapted their lifestyle to using the sea ice. They use the sea ice to travel on, to hunt on, to move around. And obviously there is a ton of different endangered charismatic megafauna that I'm sort of showing here. And this is my setup to say, Well, the megafauna is obviously the thing that we always cared about, but the thing that I've studied a little bit in recent years is what we don't care about so much, which is the smaller fauna, the base of the food web. So there is a sign. This is a picture. It's also a little muted. The picture, a satellite picture of the coast of Alaska of a giant algae bloom. And so the Arctic ecosystem feeds on these algae blooms. That's like every spring, there's these giant algae blooms that kick in, phytoplankton growing and covering the whole ocean surface. And that provides the sort of feeding base for this. But then the zooplankton come in, and then the fish come in, and then the mammals come in. And that's sort of how the feeding dynamic works in this ecosystem. And so what we've found out in recent years is that these algae blooms are actually doing really well over the last 20 years or so. Satellite data has shown that they are increasing. So I actually went with some colleagues, biology colleagues, and this is a little bit out of my wheelhouse. I'm very much a physical CI scientist, not a biologist, but the biologists and me, we went together to try and understand how the sea ice impacts these algae blooms and why they've been doing so well. And so just a couple of plots that I wanted to show. This is satellite data of chlorophyll A. It's quite fascinating. You can, from satellite data, you can get an idea of how much chlorophyll A there's in the surface of the ocean. So this is the average of June chlorophyll A, and I want to point out this little spot. Yeah, so there's a major bloom area in this region between Greenland and Svalbard. This is called Fram Strait. And if you look at, so this is 2003 to 2010, and then if you look at the more recent decade, 11 to 19, you can see that this has shifted north and expanded majorly. So there's been this great expansion of chlorophyll A and associated algae blooms in that region. We can also take the average, the spatial average of this region and plot it. Oh no, I did it again. Apologize. Where were we? Yeah. Okay. So you look at the spatial average and plot this as a time series, and you can see that it's sort of been steadily increasing over the last 20 years. And serendipitously enough, we happen to be there in May 2019 when this largest of all blooms happened. So we were on the ice collecting data. This is a couple of my students analyzing water samples, filtering water samples to understand how the sea ice, which is right next here, the sea ice impacts potentially these algae blooms. And I'm just going to quickly summarize the story that came out of this, because I do think it's fascinating. And this is not new in general. It's not a new insight that I cannot claim for myself, but I learned it for myself and I want to pass it on to you. Is that sea ice, when it melts, is very light. It doesn't have much salt in it. So it stays on top of the water column. It makes the water at the top of the ocean quite light, because sea ice, okay, let me back up one step. When sea ice grows, when it gets cold in the winter and sea ice starts to grow, it rejects most of the salt that's in the ocean water. And it forms a sea ice layer that is more or less fresh. Right? It doesn't have much salt. So when the spring comes, it melts and it is light. The salty water underneath is heavier, and so this fresh water stays up top. Now the phytoplankton that might be starting to grow in this area, they are passive tracers. They don't propel or anything, they just stay wherever the water takes them. Now if you have a lot of sea ice melt, it provides that stable surface layer, and the phytoplankton that are in there just stay in there. If you don't have a lot of sea ice melt, they get mixed around a lot more. And they do best when they are closest to the sun. So when you have a lot of sea ice melts, they're confined to that fresh surface layer, and they are exposed to a lot of sunlight. They don't get flushed down. And so the more sea ice, the closer to the sun, the more they are able to grow. And so we think that with increased amounts of sea ice melt in this region over the last 2 decades, that has really helped those algae blooms to evolve bigger and bigger. And so the next step then is to try and understand how does that matter for the higher levels of the trophic chain, right? That is a major disruption of the system, right? You're not food limited anymore. So what happens? I don't have an answer, but that's one story of what we've been working on recently. Now, the other question is, this is output from global climate models. And here we are in 2020, and just focus on this black line. This is the total meltwater that this particular model suggests we will have in this area in Fram Strait. And so there's been an increase over the last 20 years, which is in line with what I was just telling you, right? If you have an increase in meltwater, that would help the bloom. But then as the sea ice retreats further and further, you are going to lose that meltwater in the spring. So we're worried that there might be this sort of boom situation right now over the last 20 years as your meltwater increases, and then maybe followed by a bust, that once you don't have that meltwater anymore, the sea ice can't grow that well anymore. Okay, so why do we care about sea ice? Well, this is where we're getting to very relevant for us humans, very relevant questions. There's a potential new shipping routes that go through the Arctic. And they are very coveted because if you can go from Europe straight to Asia without having to go either through the Suez Canal or around Africa, you are going to cut off a lot of your ship time. I have a message in the chat. Okay, Tom, I'm gonna ignore that for now. So there is the North American routes, and then there is here the Siberian route, essentially. And the green lines are ships that are regular, and the red lines are icebreakers. And so as the sea ice retreats, more and more regular ships can potentially go through the Arctic. Comes with a whole bunch of risk as well, right? Because this is still forbidding climate, very isolated. If you crash your tanker up there, it's a whole big mess that's going to be hard to clean up. Nevertheless, Maersk, the largest shipping company in the world, sent a container ship through from Europe to Asia in 2018 that was unaccompanied by an icebreaker for the first time. So this is very much real world, real life happening at the moment. And the projections are that in the next 30 years or so, we're going to have quite a lot of availability of open ship routes in the Arctic as a result of this sea ice retreat. Another thing that's become more and more popular is tourism in the Arctic. So I don't know what flag this ship is flying under, but the numbers of tourists, and I found some data on this, up to 2019, so up to COVID. I'm sure this has plummeted since, but just from 2014 to 2015, in different regions, Svalbard, Greenland, Canada, or the Arctic, tourist numbers have exploded, right? So they've almost doubled in all of these cases just in 5 years. And it's understandable. I mean, it's absolutely gorgeous, right? The wildlife, the environment, the ice, it's very, very stunning, and it's beautiful to visit, but it also comes with risks, of course. And then there is huge potential for fossil fuel development in the Arctic. And this, again, is extremely risky and controversial. And for a while, especially under President Obama, there was more or less put a complete stop on this from an American side. The Russians, who have a big stake and a big claim on Arctic regions, have not stopped their development, and in particular, liquid natural gas is found in the Siberian on and off the shelf in huge quantities. And so this is, for example, on the Yamal Peninsula in Siberia, just recently completed this huge natural gas plant. I don't have another picture of this, but it's quite striking, and it's geopolitically very relevant right now, right? Like, the Russians are reaping the benefits of all of this type of development, and it's just a question of time until the Western countries are going to push for more hydro exploration again in the Arctic regions. There have also been some setbacks. There was a small Scottish company, Cairn. They tried to drill, and it's just very difficult. The ice, even if it's retreating, sea ice is very strong, and if it gets pushed around by winds, it makes it very hard to build oil rigs, gas rigs that are strong enough to withhold an onslaught of ice. And then, this is from a couple of months ago, start of the war in Ukraine. The Russians have been developing the Arctic region as a military environment for years, and the Americans are catching up onto that. And I have a map here that's quite helpful. So the 200 miles from the coastline is the exclusive economic zone, the EEZ, that a country can stake, and then the rest is high waters. And so here, especially this line, presents really the only direct border between Russia and the US. And in the past, this hasn't been that much of an interest because it was just ice-covered wasteland, right? But as this turns more and more into an open ocean that can be navigated, that can be controlled, there's a lot of potential for geopolitical friction and tension in this region. And on a more lighthearted note, the Russians also, I do like this quote, the perceived openness of Arctic space enables it to become a space of masculinist fantasy and adventure, which is mirrored in contemporary accounts of Arctic geopolitics. And I use that as a segue to, here's the North Pole. It's not technically in Russian waters, but nevertheless, they did take a submarine, a little robot submarine there, and planted a Russian flag on the base of the ocean at the North Pole, and then obviously made a commemorative stamp to go with that. Okay, so this is sort of my foray into the human aspect of why sea ice matters. And I want to take another 5 minutes or so, if I have time. Am I good on time? To talk a little bit more depth about one of my research topics. And basically, I think what we find from sometimes when I look at these graphs, and I could also show you a graph of temperature in the Arctic that looks just like that, only reverse, is that it's very basic physics, right? You have ice covering an ocean when it's cold, and as a climate warms, that ice will disappear. And the relationship is fairly much one-to-one, sort of like there's a very linear relationship between warming in the region and disappearance of ice. And so why do we spend so much energy and effort and time and whatnot to study these intricacies of the sea ice? And so this is a story that Mark England worked on, and I think it's a nice illustration of how little we actually know, despite this being such a simple part of the climate system. We actually don't really understand it all that well. So I showed you this figure earlier, right? It shows you how much warming, so delta TS means the change in surface temperature, how much warming you have in the tropics, in the tropical regions, when you remove the sea ice. And let me back up and try and explain to you how you get at a plot like this, right? Because this is not observed, right? We don't know what, you can't observe the change in global temperature that is due to sea ice, right? You can only observe the actual change in temperature, right? And then you can try and sort of partition that, but it's really difficult. So this plot is arrived at using some clever climate models. So what you do, I hope you're a little bit familiar with climate models. Climate models are just very complicated mathematical constructs that are trying to represent every aspect of the global climate system. And they have millions of lines of code, and they represent literally every island and chop up the globe into grid boxes and solve momentum equations and thermodynamic equations, etc. And so you run a global climate simulation, and they are obviously not exact, but they are really good. They are the best thing that we have, and they're quite powerful in the projections that they make. Now, for this particular case, what we do is we run a global climate simulation of the future, and we don't add any more CO2 to the climate. We keep the warming at the level where we are now. Okay, so you don't do any more warming, but what you do is you remove in your climate model, you just remove the sea ice, you take it out. Okay, so you take out the sea ice and you keep everything else the same, and then you look at what happens to the temperature of the globe, right? And presumably that effect is due to removing the sea ice alone. And so that is what you've done. What they've done here is basically you have a future sea ice concentration, and I apologize, this is now actually the Antarctic. So this is what the sea ice in the annual mean looks right now, and this is what it looks in the future. And so you run a climate model. Oh, it always does this. You run a climate model that starts from here, and you move the sea ice, you shift the sea ice to look like this over time, but you don't do anything else. Yeah, you don't add more CO2, you don't do any more emissions. And so then you say the result of your what the rest of your climate does is this thing. This is the effect of that simulation that I just described. Yeah? You just remove the sea ice, kept everything else constant, and you found that you have around 1, and you see, because it's the Antarctic sea ice that we've removed, you have most of the warming in the Antarctic, but in the southern hemisphere, but you even find effects of it in the northern hemisphere. Now the problem, and this is the crux of this story, is how do you remove the sea ice in the climate model? And apparently it's really difficult to do that in a way that's physically sound. Yeah, so people have tried different ways, and I'm not going to go into too much detail, but you can just add some artificial heat flux, right? You can add artificial heat flux just to where the sea ice is, and so that melts the ice artificially. Or you can, for example, you can paint the sea ice darker. Yeah, just pretend that the sea ice is darker in your model simulation, so it absorbs more solar energy and then melts more. Or you literally just take out pieces of sea ice in your simulation. You can just there's lines of code where you can take those lines of sea ice out. The problem that occurred to us with all of these methods is that you, in one way or another, you are adding artificial heat to the system by removing the sea ice. So people always thought of this as just removing the sea ice, not actually adding heat. But the only way in a climate model simulation to remove sea ice is by adding artificial heat. And this was an issue that people hadn't picked up on. And it's a really cool also like science-wise, I find it a really cool story because this is a paper by Mark from 2020. And he realized that there's this conceptual issue that you artificially heat the globe by removing the sea ice. So part of the signal is actually the energy that you put in to remove the sea ice. It's not just the loss of sea ice. So you actually have two components here, and they've been conflated. And it's interesting because there's been dozens of studies that have used exactly this methodology in high-profile journals, etc. And they all fall, at least to a little bit, fall prey to this conceptual misunderstanding. And so Mark uncovered this, and we have an idealized climate model that's only a few lines of code where we can exactly diagnose which heat is due to sea ice loss and which is due to artificially heating the system. And I can show you the results of this. And so just to orient you quickly, this is the warming here, delta TS again, and this is the latitude, so equator to pole. And so you average this over all the longitudes. And what you find is in our climate model simulation, we have a total warming of about 2 degrees at the equator and about 3 degrees, 3.5 degrees at the pole. And in this model, we understand it so well because it's mathematically straightforward. We can diagnose directly that the warming from the sea ice is just this gray line. The added warming here is the global warming simulation. So, and that's actually just a constant offset. And then we implemented in our idealized model that we understand very well, we implemented those other methods, yeah, the painting the ice black or the adding a ghost flux. We implemented those methods and looked at how much warming they produce. If they produce the right amount of warming, they would fall exactly on this gray line. But alas, they all, and I'm in the way here, well, excuse me, rather large. All these other methods that we call albedo or ghost flux or nudging methods, you can see they all overestimate the warming due to sea ice loss. And so we're currently working, this is brand new work and it's in review, and we've had very interesting conversations with a lot of within the science community because we are questioning quite a lot of work that people have done in the past and pointing to a fault in some of the simulations. But yeah, I wanted to show you this because I do think it's fascinating for a number of reasons in itself, like the complexity of climate model simulations. You have to be very careful in what you do with your climate model simulation to make sure that it is physically sound. But also, we don't understand, we don't know half of what's going on with sea ice, right? That's sort of like the moral of the story here for me is like, yes, what I was saying is like climate warms and the sea ice disappears, but I can't even tell you what the impact of sea ice loss is on the rest of the globe, right? Apparently no one can because everyone's kind of been doing it wrong. And the kind of like maybe less optimistic thing about it is that this method only shows you how much previous studies have overestimated sea ice warming due to sea ice loss. We cannot offer a better way. I cannot tell you how you should run your climate model simulation to do this properly. Just telling you that this way wasn't quite the right way. So, moral of this story is that we still don't know all that much about sea ice, even though the basic physics of, ice melting in your cocktail glass is pretty straightforward. Overall, it's part of a very complicated, complex system. So thank you very much for your attention, and I think I will leave it here with this picture.
Does anybody have any questions? Is there there any in the chat?
Let's see. The chat is quiet. Yes. One in the back. Yeah.
A quick my question is, do we know why the Arctic, we see the melting of the ice, but not the Antarctic?
Yeah, it's a very good question. Right. No, we don't actually. It is a long-standing enigma. And I actually, when I was in North Carolina, me and my collaborator Ian Eisenman at Scripps, we had a grant from the National Science Foundation to try and understand why the Antarctic has not seen a decline, because it is confusing, right? The warming of our climate is global, but somehow the southern hemisphere and the Southern Ocean in particular is not seeing that sea ice retreat. The leading theory is that it is due to winds, changes in wind pattern shifts that compensate for any larger melt. So with global warming, for example, one process is that the westerlies around Antarctica have become stronger, and that those wind patterns have acted to spread the ice out more, and that sort of counteracts the melting effect there. But we don't really know, to be honest. And it also looks like in most recent years, like the sea ice is declining in the Antarctic. And so maybe there was just some internal variability. You know, maybe it's just like the sort of the internal chaos of the system that prevented that from happening. And also there's overall a lot less land mass in the southern hemisphere. So the heat capacity is larger, which means it reacts more slowly. The Southern Ocean probably reacts overall a little bit more sluggish than the Arctic. But it's a very good question. Yeah. Yes.
Yeah. How expensive are the simulations you use? You use the computer systems at Champaign or
yeah, exactly. So you use computer systems at very large computer centers. NCAR in Boulder, for example, has a big one. So it really depends on the simulation, right? So this idealized model that I showed here, I can run this in a day on my laptop, but that's only a few lines of code. They take weeks to months. The full coupled global climate simulation takes weeks to months on supercomputers to run. In terms of CPU hours, tens of thousands, but I don't know exact numbers. Yeah. And yeah, I mean, and it's also like, you know, like it's large groups of people working on these, setting them up, getting them all ready, and then running them for months, doing something totally different for months, and then looking back and finding out what the simulation came up with. Yeah.
A follow-up question. I had listened to an interview of somebody from the UK who does global modeling, and one of the things that he has indicated that there's not enough computing power to do stochastic modeling. That is, you know, changing a whole bunch of parameters and see how sensitive it is and how things change. Is it your system you're talking about stochastic in any way, or you just set the parameters and see how it goes, but you can't do the variations to see how sensitive things are?
I think all of the stuff that I've shown today is deterministic. There's no stochastics in there, but the system is chaotic, right? So if you have the way that people probe the natural variability of the system is that you just change a tiny rounding off error at the start of your simulation in 1850, right? You just change some small variable by a tiny rounding off error, and over a short amount of time, that simulation will diverge from the other simulations. Now, it's really expensive to do each one of these simulations. So that's where it's hard to probe the full spectrum. So what people have done, there have been efforts to run what's called a large ensemble, is where you do, for example, 40 of those runs. Yeah, you do 40 simulations where you change that rounding off error in 1850 and otherwise keep everything the same. And so you have at least an ensemble of 40, and then you can do statistical analysis on that. But in order to probe the full spectrum, you would, of course, need hundreds and thousands. But yeah, so it is too expensive to run full coupled climate simulations in a quantity that would fully sample the spectrum of climate states. Yeah.
And then I think you have some in the chat.
Yeah, I have a number of questions here in the chat. Okay, let me see. You mentioned AMOC, the Gulf Stream, being affected by sea ice. What currents have been seen on the Japan current, Pacific Ocean current side? It's a good question. I don't know exactly, but overall, I would say that the impact, I would expect the impact to be quite a bit less. And that is, let me see whether I can pull up a, can't really, this is not a great map. Let me get a map here. The Bering Strait here is quite the narrow outlet. So communication between the Arctic Basin and the Pacific is much reduced compared to the Fram Strait and the connection from the Arctic to the Atlantic. So there's a lot of communication in terms of ocean currents and ice drift that along here, not so much up here. And then overall, there's also a lot more overturning in the North Atlantic than there is in the North Pacific. So I would say overall, that's why the main focus of research is on this connection here rather than across here. Let's see. Will El Nino or La Nina also impact the melting velocity across years? Why the temperature in some places decreases as sea ice melts, such as some places in Amazon? And from an economic perspective, do you think that the increasing temperature will also increase the planting availability for some crops in the originally cold areas and relieve the hunger in some places when we want to account the total effect of the melting? From Yuan Chuan. Yeah, very good questions. There have been actually, Mark, yeah, some colleagues of mine have looked, there are connections between El Nino cycles and sea ice variability. I don't know the details off the top of my head, and these teleconnections are a little difficult to diagnose. It's a little hard to tell exactly. And there's also a lot of variability in El Nino itself and in the sea ice patterns. So to link them is a challenge, but there is some research in that. And then the question about the economic perspective, yeah, I mean, that is a very interesting question. And there has been some science suggesting that more temperate climates in Siberia, etc., may improve your crop yields, etc. Overall, from my understanding and looking at this over the last 10 years or so, is that we have fairly carefully fine-tuned everything we do to the state of the climate system over the last 8,000 years, which has been very steady, right? The Holocene for 8,000 years has been remarkably uniform. And so we have very carefully built all our cities right on that coastline and developed all of our agriculture, etc., right where it has been steadily more or less the same conditions, climate, precipitation, temperature conditions for 8,000 years. And so disrupting that, it seems, from my understanding, and I'm not an expert in agriculture or anything, it does seem like a disruption typically does not yield an improvement. When you have fine-tuned your system to fit exactly one state, if you disrupt that, I would expect my yields to go down overall, globally. I'm sure there are going to be regions in Siberia that are totally barren right now that might benefit from a warming, but overall, I think climate change, it looks pretty likely that global warming overall is going to be a net issue rather than a boon for our food production. Yes.
So my question is dealing with, I'm not sure where I read this, but if all of the ice melted in Greenland, raised sea levels by up to 2 meters?
It's about 5 or 6 meters. Yeah. Yeah. Yes, that's right. And so let me X this out so you can't
So
see.
in terms of like what's really happening in Greenland, I guess, do you have any?
Yeah.
Like, how bad is it like right now?
Yeah. So Greenland is, I don't have any, wait, I mean, let me just at least pull up a picture of Greenland here somewhere. There it is, right? So it's about a 10th the volume of ice compared to Antarctica. But it is a lot more susceptible to ice loss than Antarctica has been. Part of that is because you have that warming Atlantic current coming up here, we believe. Overall, as I was showing you, the Arctic air temperatures have been increasing quite rapidly. So Greenland is losing mass fairly rapidly, but not significantly in size. I mean, it depends how you would say significantly. I think, okay, so these are the numbers that I always mangle. Over the last, so we're talking millimeters to centimeters. Over the last 100 years, I believe sea level has increased by a few centimeters, and about half of that is just the oceans expanding because they're warming. And then the other half, roughly, is from mostly mountain glaciers melting and Greenland melting, a little bit Antarctica melting as well. But the idea that, so we are getting, projections are like worst case scenario by the end of 2100 is about 1 meter of sea level rise over the next 80 years. And a substantial amount of that would come from Greenland. I don't know off the top of my head, maybe 20, 30 centimeters or so over the next 100 years or so. So it's a tricky one. Yeah? It's definitely happening. Like Greenland is accelerating also in its mass loss, but it is also, it's quite steady. I'm not steady, but it's on a human experience scale, it's slow, right? It's not like we're increasing sea levels by meters every day. So I was in North Carolina, which is sort of ground zero for sea level rise, and you could definitely tell in some of the Outer Banks, etc., where they are having real issues with, combined with increased storm surges, etc. And also, there's this fascinating thing of isostatic rebound. So there was a big ice sheet on top of North America over the last ice age, and that ice sheet, when that melted away, the Earth crust lifted up as a result, and that counteracts sea level rise in some sense. But it's complicated because the elastic rebound from removing an ice sheet is not just uplift everywhere, it's also depression in some other places because it's like a wrinkling elastic sheet. So sea level rise is actually, like, we could do a whole other lecture on sea level rise from the ice sheets. Sorry, I went on a bit of a tangent there. Yeah, well, sorry. Yeah, one more question.
How many expeditions have you been on?
I've been on not that many. I've been on one expedition to the Antarctic as a grad student, and then I've been on, I think, 4 Arctic expeditions. Yeah. So
You've done both.
I'm bipolar in that sense. Yeah. It's sort of like a polar scientist joke. My expertise is definitely more on the math and modeling side, but I try and do field work when I get to. I think it's very helpful to get a rounded understanding of the system, and it's also just really exciting. Yes.
What do you do?
So the pictures that I showed for this one was this collaboration with the biologists. So we were looking at sea ice conditions and water conditions in here. I have a picture here. Yeah, so there's me standing on the ice, taking an ice core. So we were trying to understand better how the sea ice impacts and is linked to the phytoplankton blooms. So we take water samples, we analyze them for what's in the water. We take ice core samples. We look at how old the ice is, how thick it is, how much snow there's around. We also had some people observing marine mammals, looking at zooplankton. So in situ work is complicated, right? Because we can do so much these days with satellites, so much better than by actually going. So you need a very good reason to go and study something very particular in order for it to make sense. So this was a very specific scenario where we wanted to look at what's happening in the water column right next to the ice. What are the animals that are in there? What are the plants? And how much seawater is actually where they live. And in other cases, I've studied the breakup of icebergs, and we've looked at snow deposition on sea ice. So it's these smaller scale things that you can't really understand from remote sensing from satellites at all. So, yeah.
So with increased algae blooms, it could probably help the fishing industry and the whales, right?
So, yeah, potentially. Maybe, yeah.
More food, right?
They might provide more food, yeah. There's also, I know, for example, for corals, it's not that great. There's this quote like slippery slope to slime. When you have too much algae, it like suffocates the corals, right? So not more of something is not always a good thing. In this case, it might be great right now. Who knows? Yeah, this is sort of like it might be. Yeah, I don't say that this is a negative or a positive thing. I don't really know myself, but it is a dramatic change. So it'll be interesting to see. I would love to find out whether it's who benefits or not. Yeah.
What is the $1 million question in your research area or in your like general?
Sorry, say that again. What is
the $1 million?
The $1 million question? Oh. That's a good. $1 million question. I don't. Yeah, I think ultimately it's the prediction of when we lose the sea ice. Like, I think that's what people always come back to. I don't know. The reason why I'm hesitating is I don't know whether it's the most exciting or interesting question. I mean, the sea ice, I can more or less, I reckon I can more or less draw a line from this down to here, and it will be somewhere over here, right? But that is the thing. I mean, like from all I've shown you today, right? Like economically, etc. Like that's what people care about. When is the ice free? When can we start shipping? When do we want to go drilling? How do we have to prepare? When do we need to worry about the Russians using their warships in the Arctic, etc. Right? So, I mean, no, it's a little stressful. I will say this. I know that these stay online, these talks, I don't know, you're posting them and they're up there for eternity, right? So like, yeah, hi future Till, like, good job navigating these questions. There was one more, maybe. Oh yeah, two more in the chat. Let's see. Matt, Tom says thank you, and one more thank you. So, okay, thank you.